Hi, welcome to Sunil Maths tutorial, functional analysis, class number 8. So, in this video, we learn some definitions and one theorem. Let us see the definition: continuous linear transformation. Continuous linear transformation. Let capital N and N dash be two normed linear spaces. Be two normed linear spaces. And capital T maps N into N dash be a linear transformation. Then this linear transformation capital T is said to be continuous. Is said to be continuous. The linear transformation capital T is said to be continuous if it satisfies one condition. If it satisfies one condition, xn converges to x in capital N implies xn converges to x in capital N implies t of xn converges to t of x in n dash. In n dash. I repeat the definition. Observe that continuous linear transformation. Capital N and N dash be two normed linear spaces. T maps N into N dash be a linear transformation. Then this linear transformation T is said to be continuous linear transformation if it satisfies one condition. When xn converges to x in capital N implies as t of xn converges to t of x in n dash. It means whenever the elements converges in the domain, then the corresponding images are also converges in the codomain. Here n is the domain and n dash is the codomain. Whenever the elements in the domain xn converges to x, then the corresponding images also converges to their corresponding images. So right, remember this condition which is important for us. So whenever xn converges to x, whenever xn converges to x in capital N implies t of xn converges to t of x in n dash. In n dash. So right, we go for next definition, bounded linear transformation. Same theory. You see, let us take capital N and N dash be two normed linear spaces. Be two normed linear spaces. And capital T maps capital N into N dash be a linear transformation. Be a linear transformation. Then this T is called bounded. This T is called bounded if there exists a real number. If there exists a real number k greater than or equals to 0 such that norm t of x is always less than or equals to k into norm x for all x belongs to capital N. For all x belongs to capital N. Then we say that T is bounded. Here capital K is called bound. Capital K is called bound for T. Capital K is called bound for T. And the T is called bounded linear transformation. I repeat the definition, please observe that. So a linear transformation capital T which maps from one normed linear space to another normed linear space n into n dash is called a bounded set or is called a bounded linear transformation, not set, bounded linear transformation. If there exists a real number k greater than or equals to 0, satisfying the condition norm t of x less than or equals to k into norm x for all x belongs to capital N. Here the real number k is called, bound. Here the real number k is called bound for t, and t is called bounded linear transformation. So right, remember these two definitions. One is continuous and the second one is bounded. Now we prove one very important theorem. In the functional analysis according to these linear transformations. Let capital N and N dash be two normed linear spaces, and T maps N into N dash be a linear transformation. Then the following four conditions are equivalent to one another. The following four conditions are equal to one another. T is continuous, and T is continuous at origin in the sense that xn converges to 0 implies T of xn converges to 0. There exists a real number k greater than or equals to 0 such that norm T of x is less than or equals to k into norm x, which is nothing but this third condition is nothing but bounded condition. Third condition is nothing but bounded one. And the last one, fourth one, if S is equals to set of all elements x such that norm x less than or equals to 1, is a closed unit sphere in capital N, then its image, the image of S, T of S, is a bounded set in N dash. So observe the four conditions. These conditions are equivalent to one another. So we prove this theorem like this. Condition 1 implies condition 2, and condition 2 implies condition 1. It means condition 1 implies and implied by 2. And then we prove 2 implies 3, and then we prove 3 implies 2. It means condition 2 implies and implied by 3, and finally we prove that 3 implies 4. Condition 3 implies 4, and condition 4 implies 3. It means 3 implies and implied by 4. These three now according to all these three, we conclude that all the four conditions are equivalent to one another. Let us start our proof. So 1 implies 2. Let us take capital T is continuous. Now we write the definition of continuous one. Xn converges to x implies as T of xn converges to T of x. In particular, replace that x by 0. It means xn converges to 0, which implies T of xn converges to T of 0. Here what is T? Capital T is a linear transformation. One of the property of linear transformation, T of 0 is equals to 0. This condition implies as T of xn converges to 0. It means what we show that xn converges to 0 implies as T of xn converges to 0. This shows us capital T is continuous. At origin. So this proves 1 implies 2. Now the next one is 2 implies 3. 2 implies 1. We prove that 2 implies 1. So assume that. Let us take T is continuous at origin. Let capital T is continuous at origin. What it means? Xn, that is xn converges to 0 implies T of xn converges to 0. Now we prove that suppose xn converges to x. If xn converges to x, then xn minus x converges to 0. xn minus x converges to 0. What it means? T of xn minus x converges to t of 0. Now we use two properties of linear transformation. Capital T is a linear transformation, which implies as T of alpha minus beta is equals to T of alpha minus T of beta. By applying that condition, here it becomes T of xn minus T of x tends to, here it is T of 0. T of 0 is equals to 0, this one. So which implies as, this condition again implies as T of xn converges to T of x, converges to T of x. What it means? We take that xn converges to x. We prove that T of xn converges to T of x. This condition shows us capital T is continuous. Capital T is continuous. Hence, this condition implies as 2 implies 1. 2 implies 1. Now you observe that in the first case we prove that 1 implies 2, and in the second case we prove that 2 implies 1. Therefore, finally we conclude that 1 implies and implied by 2. 1 implies and implied by 2. Now we are going to prove 2 implies 3. 2 implies 3. For this, let us take or let us assume, anyone, let us take or let us assume T is continuous at origin. T is continuous at origin. If T is continuous at origin, it means the term xn or the sequence xn converges to 0 implies as T of xn converges to also 0. T of xn converges to 0. We have to prove that norm T of x, is less than or equals to k into norm x. This is our aim to show that. So assume the contradiction point. Suppose that there exists a real number k greater than or equals to 0 such that norm T of x is greater than k into norm x. Actually, we have to show that the converse part for all x belongs to capital N, but we assume the contradiction point. From this condition, from this inequality, you observe that there exists a positive integer small n such that norm T of xn is greater than n into norm xn. So what it means? Norm T of xn divided by n into norm xn is greater than 1. Applying the norm properties, you can write like this. Norm of T of xn by n into norm xn is greater than 1. So define another sequence yn is equals to xn divided by n into norm xn. By applying this inequality here, you get norm T of yn is greater than 1. Now you observe the limit n tends to infinity, yn is equals to limit n tends to infinity xn by n into norm xn. Everybody knows that 1 by n tends to 0 as n tends to infinity. So by applying that condition, this limit becomes 0. It means limit n tends to infinity yn is equals to 0. It means the sequence, there exists a sequence yn that belongs to capital N such that norm T of Yn is greater than 1. Norm T of Yn is greater than 1. What it means? The sequence Yn converges to 0, but T of Yn does not converges to 0. You see, limit Yn is 0. It means Yn converges to 0. Yn converges to 0. But T of Yn, norm T of Yn greater than 1 means T of Yn does not converges to 0. Does not converges to 0. This is a contradiction. This is a contradiction. Because already we know that whenever xn tends to 0 implies T of xn also tends to 0, because T is continuous at origin. This is a contradiction to the fact that T is continuous. That is this one. So our assumption is wrong. What is our assumption? This one. Suppose that there exists a constant k greater than or equals to 0 such that norm T of x greater than k into norm x. This is wrong. So what is right now? Therefore, there exists a real number k greater than or equals to 0 such that norm T of x is less than or equals to k into norm x for all x belongs to capital N. This condition shows us capital T is bounded. Hence, this proves that condition 2 implies 3. Now we prove that, next we have to prove that 3 implies 2. Next we have to prove that 3 implies 2. To prove that 3 implies 2, assume that there exists a real number k greater than or equals to 0 such that norm T of x is less than or equals to k into norm x for all x belongs to capital 1. Let it be equation number 1 or equation number A, some inequality equation A. Now let us take xn be a sequence in the normed linear space capital N which converges to 0. It means xn tends to 0 as n tends to infinity in capital N. It means norm xn tends to 0. Now from equation number A, norm xn tends to 0 means norm of T of xn is less than or equals to k into norm xn. Because of norm xn tends to 0 implies T of xn, norm T of xn also tends to 0. This shows us capital T is continuous at origin. This proves condition number 2. Therefore, 3 implies 2 is proved. Hence, already we proved that 2 implies 3. Here we prove that 3 implies 2. Therefore, we conclude that 2 implies and implied by 3. Now we are going to prove 3 implies 4. So again, suppose that, assume condition number 3. Suppose that there exists a real number k greater than or equals to 0 such that norm T of x is less than or equals to k into norm x for all x belongs to capital N. This is condition number 3. You have to prove that the set S is bounded. So by data that S is defined like this: set of all elements X such that norm X is less than or equals to 1. Norm X is less than or equals to 1. Then now write the image T of S. T of S is equals to T of S is equals to the set of all images T of X such that X belongs to S. Such that X belongs to S. T of X, you can use norm T of X such that X belongs to S means norm X is less than 1. Norm T of X, here you observe that norm T of X is less than or equals to K into norm X. So K into norm X such that norm T of X is less than or equals to K. This shows us this set is completely less than or equals to K. Hence we show that T of S is less than or equals to K. Therefore we conclude T of S is bounded set. T of S is bounded set in N dash. T of S is bounded set in N dash. So right, this condition proves as 3 implies 4. This condition implies as 3 implies 4. So we assume that capital T is bounded. We prove that T of S is bounded. So next we are going to prove 4 implies 3. We have to show that 4 implies 3. To prove this, we define certain things. By data, they given that S is equals to X such that norm X less than or equals to 1 is a closed sphere. Is a closed sphere in capital N. Is a closed sphere in capital N. And T of S is a bounded set. T of S is a bounded set in N dash. Remember that. S is closed sphere in N and T of S is bounded set in N dash. Now we have to prove that. Norm T of X less than or equals to K into norm X. K into norm X. So right, to prove this, we use two different conditions. If X is equals to 0, then there is nothing to prove because norm X also equivalent to 0. T of 0, norm T of 0 is also equivalent to 0. So obviously the condition holds. Norm T of X is less than or equals to K into norm X. Whenever X is equals to 0, the condition is trivially true. If X equals to 0, then there is nothing to prove. This condition is trivially true. So right, we define X not equals to 0. If X not equals to 0. Now to prove our inequality, we define a set. We define an element. Y is equals to X by norm X. Now you apply that. Norm Y is equals to norm X by norm X. This can be written as norm X by norm X. This can be written as 1. It means norm Y is equals to 1. If norm Y is equals to 1, by applying the definition of S, what is S? S is the set of all elements whose norm is less than or equals to 1. Here norm Y is equals to 1 implies as Y belongs to S. If Y belongs to S, then obviously T of Y belongs to T of S. T of Y belongs to T of S. T of Y belongs to T of S and T of S is bounded. If T of S is bounded, from this you can conclude that T of Y is less than or equals to K. If T of Y is less than or equals to K, what is Y? T of X by norm X is less than or equals to K. This can be written as 1 by norm X into T of X. I mean I mean, you can write it as norm T of x. According to here, if T of y is less than or equals to k, implies as norm T of y is less than or equals to k also. So here also you can use norm. So you can 1 by norm x into norm T of x is less than or equals to k. Now shift this term to this side, you simply get norm T of x is less than or equals to k into is less than or equals to k into norm x. This is true for all x belongs to capital N. Hence we conclude that T is bounded. T is bounded. This proves condition number 4 implies 3. Hence we prove that 3 implies and implied by 4. Now you see carefully here 3 implies and implied by 4 and 3 implies and implied by 4. Here we show that from this here 2 implies and implied by 3, 2 implies and implied by 3, and here we show that 1 implies and implied by 2. 1 implies and implied by 2. From all these three conditions, we conclude that all these four properties are equivalent to one another. T is continuous implies and implied by. T is continuous at origin implies and implied by. T is bounded implies and implied by. The images of a closed sphere, unit spheres, are also bounded in N dash. These four conditions are equivalent to one another whenever the T is a linear transformation. In the next video, we'll learn one more theorem. Wish you all the best. Keep learning.